What if everything you thought you knew about how the universe works was just the surface of something far stranger? What if the speed of light and gravity, the two fundamental forces that shape every moment of your existence, aren't separate phenomena at all, but two faces of the same cosmic coin? In 2023, physicist Dr. Erik Verlinde at the University of Amsterdam published findings that sent shockwaves through the physics community. His research suggests that gravity might not be a fundamental force at all, but an emergent property of something deeper, something intimately connected to the cosmic speed limit we call light speed. But here's what will absolutely blow your mind. If he's right, then black holes aren't what we think they are. Time travel becomes theoretically possible, and the fabric of reality itself is far more malleable than we ever imagined. Today, we're going on a journey that will fundamentally change how you see the universe. We're going to explore a radical new framework that could unite Einstein's two greatest discoveries into a single, elegant theory. And by the end of this video, you'll understand why some of the brightest minds in physics believe we're on the verge of the biggest paradigm shift since Einstein himself walked into the patent office in 1905. But before we dive into the deep end, I need you to do something. Hit that like button right now. Seriously, because what you're about to learn is going to challenge everything you think you know about reality. And I need to know you're ready for this journey. Subscribe if you haven't already, and drop a comment telling me where in the world you're watching from and what time it is right now. Are you in Mumbai at 2 a.m., unable to sleep because your mind is hungry for knowledge? Are you in New York during your lunch break? Let me know, because this community spans the globe, and I want to see how far this mind-bending journey reaches. All right, let's begin with something that seems simple, but hides a universe of complexity. Light. You flip a light switch. The room illuminates instantly, or so it seems. But here's the truth that most people never think about. That light didn't actually reach your eyes instantaneously. It traveled at exactly 299,792,458 meters per second. Not 299,792,457. Not 299,792,459. Exactly that speed. Every single time, in every direction. Under every circumstance. But why? Why does light have a speed limit at all? Why not infinite speed? And here's the really weird part. Why is it the same speed for everyone, no matter how fast they're moving? Think of it like this. Imagine you're on a train moving at 100 kilometers per hour, and you throw a ball forward at 50 kilometers per hour. To someone standing on the platform, that ball is moving at 150 kilometers per hour, right? The speeds add up. That makes intuitive sense, but light doesn't work that way. If you're on a spaceship moving at 99% the speed of light, and you shine a flashlight forward, that light doesn't travel at 199% the speed of light. It travels at exactly 100% the speed of light. And here's the kicker. To someone standing still watching you zip by, that same beam of light also travels at exactly 100% the speed of light from their perspective too. This is what broke physics in 1905. This is what made Albert Einstein, a 26-year-old patent clerk with no access to a laboratory or university resources, realize that something fundamental about our understanding of space and time had to be wrong. Einstein's insight was revolutionary. The speed of light isn't just a speed, it's the speed of causality itself. It's the rate at which cause and effect can propagate through the universe. Nothing can go faster because there is no faster in the structure of spacetime. It's like asking what's north of the North Pole. The question itself doesn't make sense. But Einstein didn't stop there. 10 years later, in 1915, he published his general theory of relativity, which reimagined gravity not as a force, but as the curvature of spacetime itself. Picture a bowling ball on a trampoline, creating a depression that causes smaller balls to roll toward it. That's what mass does to spacetime. The sun doesn't pull the Earth. The Earth is simply following the straightest possible path through curved spacetime, and that path happens to be in orbit. Here's where things get interesting. These two theories, special relativity, which deals with the speed of light and constant velocity, and general relativity, which deals with gravity and acceleration, are Einstein's two masterpieces. They've been tested thousands of times. They work. GPS satellites wouldn't function without accounting for both theories. We've detected gravitational waves, ripples in spacetime itself, using detectors so sensitive they can measure distortions smaller than a proton. But here's the problem that's haunted physics for over a century. These two theories don't play nice with quantum mechanics, the physics of the very small. And nobody, not Einstein, not Stephen Hawking, not anyone, has been able to fully unite them into one coherent framework. Until maybe now. Let me tell you about something called entropic gravity and why it might be the key to everything. But to understand it, we need to talk about something that seems completely unrelated. The steam rising from your morning coffee? When you boil water, you're not commanding individual water molecules to rise. You're adding energy to a system, and the molecules naturally organize themselves in a way that increases entropy, the measure of disorder in a system. The steam rises because that's the configuration that allows the most random distribution of molecular motion. It's spontaneous. It's emergent. No fundamental rising force is pushing the steam upward. It's just what happens when you have that many molecules and that much energy. In 2010, Eric Verlinde proposed something radical. What if gravity works the same way? What if gravity isn't a fundamental force at all, but an emergent phenomenon arising from the tendency of the universe to maximize entropy? This sounds insane at first. Gravity feels pretty fundamental when you jump off a diving board. But Verlinde showed mathematically that if you treat space itself as having microscopic information encoded in it, almost like pixels on a screen, then gravity naturally emerges from the tendency of this information to distribute itself in the highest entropy configuration. Think of it like this. Imagine the universe as a cosmic computer, and every tiny region of space contains information, bits of data about what's there and what's happening. When you have mass, you're essentially creating information density. And just like how gas naturally spreads out to fill a container, information wants to spread out too. That spreading, that redistribution of information, manifests as what we experience as gravity. But here's where it connects to the speed of light. Information can't propagate faster than light speed. That's not just a rule. It's baked into the structure of causality. So if gravity is really about information redistribution, then gravity and light speed are fundamentally linked. They're two aspects of the same underlying reality, the flow of information through spacetime. This is mind-blowing because it suggests that the cosmic speed limit and the force that holds your feet to the ground are two faces of the same phenomenon. They're both about how information moves through the universe. Now, you might be thinking, okay, this is interesting theoretical stuff, but does it actually explain anything new? Does it make predictions we can test? And that's exactly the right question to ask. Because here's what will absolutely shock you. This framework predicts something different about how galaxies rotate, something that might explain one of the biggest mysteries in modern cosmology without invoking dark matter at all. Let me set the stage for what's coming next. In the 1970s, astronomer Vera Rubin made observations that broke cosmology. She was studying how galaxies rotate, and she discovered something impossible. The outer edges of galaxies were rotating just as fast as the inner regions. This shouldn't happen. According to our understanding of gravity, stars far from the galactic center should be moving much slower, like how Neptune orbits the Sun much slower than Mercury. But they weren't. The galaxies were rotating like solid disks, not like solar systems. The only explanation that made sense was that there must be enormous amounts of invisible matter, dark matter, creating extra gravitational pull. We've been searching for dark matter particles for decades. We've built detectors deep underground, sent satellites into space, run countless experiments. And we've found nothing. Zero. Not a single dark matter particle detected. What if we've been looking for the wrong thing? What if the anomalous galactic rotation isn't caused by invisible matter, but by a modification in how gravity itself behaves at cosmic scales? And what if that modification emerges naturally from the connection between gravity and light speed in an entropic framework? But I'm getting ahead of myself. Before we can understand how this new theory might revolutionize cosmology, we need to understand what light and gravity actually are at a much deeper level. We need to go back to the beginning, to the moment when humans first realized that light was something physical, something that could be studied and measured. And that journey begins in a place you'd never expect, with a Danish astronomer trying to figure out why Jupiter's moons weren't where they were supposed to be. In 1676, Ole Ragnar was obsessively observing Io, one of Jupiter's moons. Io orbits Jupiter every 42.5 hours, like clockwork. Ragnar kept meticulous records of when Io would disappear behind Jupiter and when it would re-emerge. And he noticed something strange. The timing was off. When Earth was moving toward Jupiter in its orbit, Io would emerge earlier than predicted. When Earth was moving away from Jupiter, Io would emerge later than predicted. The difference was only about 22 minutes over 6 months, but Ragnar realized what this meant. Light wasn't instantaneous. It had a finite speed. The light from Io took extra time to reach Earth when Earth was farther away. By calculating the difference in Earth's position and the timing discrepancies, Ragnar calculated that light traveled at about 220,000 kilometers per second. It wasn't perfectly accurate, but it was the first time in human history anyone had measured the speed of light. Think about how revolutionary this was. For thousands of years, humans assumed that light was instantaneous, that the act of seeing was immediate. Ragnar proved that there's a delay, a cosmic lag between when something happens and when we see it. When you look at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. When you look at the nearest star system, Alpha Centauri, you're seeing it as it was 4.37 years ago. When you look at the Andromeda Galaxy, you're looking 2.5 million years into the past. The universe isn't just spread out in space. It's spread out in time. And light is the messenger that carries information across that space-time gulf. But here's what really matters. Ragnar's discovery proved that light is physical. It exists. It travels. It has properties. And if it has properties, it can be studied, measured, and understood. Over the next 2 centuries, scientists began to unravel what light actually is. In the early 1800s, Thomas Young performed his famous double-slit experiment, shining light through 2 narrow slits and observing the pattern on a screen behind. If light were just particles, you'd expect to see 2 bright bars. But that's not what Young saw. He saw an interference pattern, alternating bright and dark bands, proof that light was behaving like a wave. Think of it like ripples on a pond. When 2 sets of ripples meet, they interfere with each other. Where 2 crests meet, you get a bigger crest. Where a crest meets a trough, they cancel out. Young's interference pattern proved that light was doing the same thing. Light was a wave, but a wave in what? Sound waves are vibrations in air. Ocean waves are vibrations in water. What was light vibrating in? Scientists at the time proposed the existence of a luminiferous ether, an invisible substance that permeated all of space and allowed light waves to propagate. This seemed reasonable. After all, every wave they'd ever studied needed a medium to travel through. Then, in the 1860s, James Clerk Maxwell unified electricity and magnetism into a single theory. His equations showed that oscillating electric fields create magnetic fields, and oscillating magnetic fields create electric fields. These fields could sustain each other, creating a self-propagating wave. And when Maxwell calculated the speed of this electromagnetic wave, it came out to exactly the speed of light. Maxwell realized something profound. Light is an electromagnetic wave. It's not a vibration in some mysterious ether. It's a self-sustaining oscillation of electric and magnetic fields dancing together as they propagate through space. This was beautiful. This was elegant. But it created a new problem. If light is a wave in electromagnetic fields, not in a medium, then what determines its speed? Why exactly 299,792,458 meters per second? The answer, it turns out, comes from the fundamental constants of electromagnetism, the permittivity and permeability of free space. These constants determine how strong electric and magnetic fields are, and when you combine them in Maxwell's equations, out pops the speed of light. It's not arbitrary. It's fundamental. It's baked into the electromagnetic nature of reality itself. But there's something even deeper here, something that connects to gravity in a way Maxwell never imagined. Those fundamental constants, the ones that determine light speed, are actually telling us something about the structure of spacetime itself. They're not just properties of electromagnetism. They're properties of the fabric of reality. And that brings us to 1905, to Einstein's miracle year, when a 26-year-old patent clerk published 4 papers that changed physics forever. One of them introduced special relativity, and it started with a simple question. What if the speed of light is the same for everyone, regardless of how they're moving? This question seems innocent, but its implications are reality-shattering. If light speed is constant for all observers, then something else has to give. And what gives is space and time themselves. Einstein realized that if you're moving relative to me, your clocks tick slower from my perspective, and your rulers are shorter from my perspective. Time dilation and length contraction aren't illusions. They're real geometric properties of spacetime. Time and space aren't fixed, absolute quantities. They're flexible, relative, interconnected. And here's the key insight that connects to our modern theory. Einstein's equations show that the speed of light isn't just a speed. It's a conversion factor between space and time. It tells you how much time equals how much space. In natural units, physicists actually set c, the speed of light, equal to 1, because space and time are really the same thing measured in different ways. Think of it like this. Imagine you're looking at a map with north-south and east-west axes. If you rotate the map, what was pure north becomes a mixture of north and east. The total distance doesn't change, but how much is north versus east does. Spacetime works the same way. If you change your velocity, you're rotating through spacetime. What's pure time in one frame becomes a mixture of time and space in another frame. Light speed is the conversion factor that tells you how to do this rotation. But Einstein wasn't done. 10 years later, he published general relativity, which extended this insight to include gravity and acceleration. And this is where things get truly strange. In general relativity, gravity isn't a force pulling on objects. It's the curvature of spacetime itself. Massive objects like the sun or Earth create curves, dips, and warps in the fabric of spacetime. Objects moving through this curved spacetime follow geodesics, the straightest possible paths, which from our perspective look like orbits and falling. Here's an analogy that makes this concrete. Imagine you're drawing a straight line on a flat piece of paper. Easy. Now imagine drawing a straight line on a sphere, like Earth. If you start at the equator and draw northward, always going as straight as possible, you'll eventually reach the North Pole. But if someone else starts at a different point on the equator and also draws straight northward, they'll reach the same North Pole. Your two straight lines converged, even though neither of you turned. That's what curved space does. That's what gravity is. Einstein's field equations tell you exactly how mass and energy curve spacetime. And once you know the curvature, you can predict how objects will move through it. These equations have been tested to incredible precision. We've measured the gravitational redshift of light climbing out of Earth's gravity well. We've observed the precession of Mercury's orbit, which Newton's gravity couldn't explain, but Einstein's predicted perfectly. We've even photographed the shadow of a black hole, the ultimate manifestation of extreme space-time curvature. But here's where the connection to light speed becomes crucial. In general relativity, the speed of light isn't just constant in special relativity's flat spacetime. It's locally constant everywhere, even in curved spacetime. No matter where you are, no matter how strong the gravitational field, if you measure the speed of light right there, you'll always get c. However, and this is critical, the path light takes is affected by spacetime curvature. Light doesn't travel in straight lines through the universe. It follows the curves. This is called gravitational lensing, and we observe it all the time. When light from a distant galaxy passes near a massive galaxy cluster on its way to us, the spacetime curvature bends the light, creating multiple distorted images of the background galaxy. We've used this effect to map the distribution of mass in the universe. So light speed and gravity are connected in Einstein's theory. Gravity tells spacetime how to curve, and that curvature tells light how to move. But they're still separate things. Light speed is about special relativity and the structure of flat spacetime. Gravity is about general relativity and spacetime curvature. Or so we thought. What if I told you that at a deeper level, light speed and gravity aren't just connected, but are actually two manifestations of the same underlying phenomenon? What if the cosmic speed limit and spacetime curvature are both emergent properties of something more fundamental? This is where our journey gets really interesting. But to understand the new theory, we need to talk about information. Not information in the everyday sense of data on your phone or facts in a book. I'm talking about information in the deepest physical sense, the fundamental bits of reality itself. And that requires us to take a detour into one of the strangest places in the universe, the edge of a black hole. Stay with me, because what you're about to learn will change everything. But first, hit that subscribe button if you haven't already, because we're just getting started, and trust me, you don't want to miss where we're going next. In the 1970s, physicist Jacob Bekenstein was puzzling over a paradox. Black holes seem to violate the second law of thermodynamics, the principle that entropy, disorder, always increases in a closed system. Here's the problem. If you throw a hot cup of coffee into a black hole, that coffee has entropy, thermal energy, disorder. But once it crosses the event horizon, the boundary beyond which nothing can escape, that entropy seems to disappear from the universe. The black hole doesn't look any different from the outside. It's just a bit more massive. This bothered Bekenstein deeply. The second law of thermodynamics isn't just some rule. It's one of the most fundamental principles in physics, perhaps the most fundamental. As physicist Arthur Eddington said, if your theory is found to be against the second law of thermodynamics, I can give you no hope. So Bekenstein proposed something radical. What if black holes have entropy themselves? What if the entropy of the coffee doesn't disappear, but instead gets added to the entropy of the black hole? But where would this entropy be stored? In the swirling chaos of matter inside the black hole? Bekenstein realized that couldn't be right, because once something crosses the event horizon, we can never get information about it back out. The entropy had to be somewhere we could theoretically access, somewhere associated with the black hole, but not hidden inside it. His answer: the entropy is stored on the event horizon itself, the surface of the black hole. And here's the kicker. The amount of entropy is proportional to the area of the event horizon, not the volume. This is weird, really weird. Think about it. If you have a box of gas, the entropy depends on the volume, on how much gas you have. But for a black hole, the entropy depends on the surface area. It's as if all the information about what's inside the black hole is somehow encoded on its surface, like a hologram. Stephen Hawking initially opposed this idea, But then in 1974, he made a discovery that not only validated Bekenstein's insight, but deepened the mystery even further. Using quantum field theory and curved spacetime, Hawking showed that black holes aren't perfectly black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Here's how it works. In quantum mechanics, empty space isn't truly empty. It's seething with virtual particle-antiparticle pairs that pop into existence and annihilate each other almost instantly. This happens everywhere, all the time. But near the event horizon of a black hole, something special can happen. If a virtual pair appears right at the horizon, one particle might fall into the black hole while the other escapes. To an outside observer, it looks like the black hole is emitting particles, radiating energy. This radiation has a temperature, and temperature means entropy. Hawking calculated this temperature precisely, and it matched Bekenstein's formula for black hole entropy. This was a triumph. It proved that black holes really do have thermodynamic properties. But it also created a crisis, the information paradox. If black holes evaporate by emitting Hawking radiation, and if this radiation is purely thermal, with no information content, then what happens to all the information about everything that fell into the black hole? Does it just vanish when the black hole finally evaporates completely? That would violate quantum mechanics, which insists that information is never truly destroyed. Every quantum process is reversible in principle. If you know the final state precisely enough, you can work backward to figure out the initial state. But if information disappears into black holes, this fundamental principle breaks down. Physicists have wrestled with this paradox for decades. Hawking himself initially believed that information was indeed destroyed, that quantum mechanics needed to be modified. But most physicists found this unacceptable. Information conservation is too fundamental. The resolution, most physicists now believe, involves the holographic principle. This is one of the most mind-bending ideas in modern physics, and it's crucial for understanding the connection between light speed and gravity. The holographic principle states that all the information contained in a volume of space can be encoded on the boundary of that region, on its surface. It's named after holograms, those 2D surfaces that encode 3D images. According to the holographic principle, our 3D universe might actually be a projection from information encoded on a 2D surface at the edge of the universe. Think of it like this. Imagine you're playing a video game. The game world seems three-dimensional, but actually, all the information is stored in the computer's memory as a series of bits, essentially a 2D array of data. The 3D world is a projection, a representation of that underlying information. The holographic principle suggests reality works similarly. The 3D space we inhabit might be a projection of information fundamentally stored in a lower dimensional form. This is absolutely wild, and it has profound implications for how we understand light speed and gravity. If reality is holographic, if information is fundamentally stored on surfaces rather than in volumes, then the flow of information through spacetime becomes the primary thing. And both light speed and gravity emerge from properties of this information flow. This brings us back to Eric Verleen's entropic gravity. Verleen took the holographic principle seriously and asked, if space-time is emergent from information, what would gravity look like? His answer: gravity is the entropic force that arises when you have information distributed on holographic screens throughout space. When you move an object, you change the distribution of information, and the universe naturally pushes back toward configurations with higher entropy. That pushing back is what we experience as gravity. Verleen's insight is that massive objects in spacetime create similar situations. They create information gradients, and space naturally flows toward configurations that maximize entropy. That flow manifests as acceleration toward the massive object, which we call gravity. But here's where it connects to light speed. Information can only flow at a maximum speed, and that speed is c, the speed of light. This isn't a separate law. It emerges from the holographic structure of spacetime itself. The speed of light is the rate at which information can be transferred from one holographic screen to another. Think of spacetime as being made up of countless overlapping holographic screens, surfaces encoding information about what's nearby. When something changes, when information updates, that update can't propagate faster than light because the screens themselves have a maximum information transfer rate. That rate is determined by fundamental Planck scale properties of spacetime. So in this framework, light speed and gravity are intimately connected. They're both about how information flows through the holographic structure of spacetime. Light speed is the maximum information transfer rate. Gravity is the entropic force arising from information gradients. Two sides of the same coin. Now, you might be thinking, okay, this is philosophically interesting, but is it just interpretation? Or does it actually predict something different? Remember Vera Rubin's observations of galactic rotation curves? In the entropic gravity framework, gravity behaves slightly differently at low accelerations, exactly the regime where galaxies rotate. Verleen's equations predict that at these scales, the apparent gravitational force is stronger than Newton or Einstein would predict, not because there's dark matter, but because the entropic contribution to gravity becomes significant. When you run the numbers, entropic gravity predicts rotation curves that match what we observe without invoking any dark matter at all. The galaxies are rotating exactly as they should if gravity is entropic and information-based. This is controversial. Dark matter is the mainstream explanation, and there's other evidence for it beyond rotation curves, like gravitational lensing and the cosmic microwave background. But the fact that entropic gravity naturally predicts the right behavior without adding any new particles or parameters is striking. Even more interestingly, entropic gravity might explain recent observations from the James Webb Space Telescope that have puzzled cosmologists. JWST has been finding fully formed galaxies much earlier in the universe's history than our models predict. If gravity behaved slightly differently in the early universe due to entropic effects, galaxy formation could have proceeded faster, explaining these observations. But perhaps the most profound implication is what this theory suggests about the nature of reality itself. If spacetime is emergent, if it arises from underlying information, then the universe is fundamentally computational. Not in the sense of being a simulation running on some alien computer, but in the sense that information processing is the most fundamental thing that exists. And here's what will truly blow your mind. If spacetime itself is emergent, then the distinction between space and time, the cosmic speed limit, even causality itself, might not be fundamental. They might be emergent properties that only apply within our particular informational structure. This suggests that at the deepest level, beyond spacetime, there might be structures where our usual concepts don't apply. Regions where cause and effect aren't clearly defined, where past and future are interchangeable, where the very notion of location doesn't make sense. We're not just talking about weird physics here. We're talking about the possibility that the universe we experience, with its clear past and future, its definite locations, its separation between cause and effect, is just one possibility, one way that information can organize itself. There might be other possibilities, other ways information could be structured that would create entirely different experiential realities. And the boundary between these possibilities might not be as firm as we think. But I'm getting way ahead of myself. Before we can explore these mind-bending implications, we need to understand exactly how this informational framework works. We need to dive deeper into what information actually means in physics and why treating it as fundamental changes everything. That's what we're going to explore next. And trust me, once you understand this, you'll never look at reality the same way again. But before we continue, I want to hear from you. Drop a comment. Does the idea that reality is fundamentally informational resonate with you? Or does it seem too abstract? Let's have a conversation about this. because understanding these concepts together makes the journey even more powerful. Now, let's talk about information in a way that will make it concrete and real. When physicists talk about information, they're not talking about meaning or knowledge. They're talking about something much more fundamental: distinguishability. Information, in the physical sense, is about how many different states a system can be in and how you tell them apart. The basic unit of information is the bit, which can be in one of two states, 0 or 1, on or off, up or down. A single bit tells you the answer to a yes or no question. 2 bits can represent 4 different states, 0001, 10, 11. 3 bits give you 8 states. Every time you add a bit, you double the number of distinguishable states. Now here's the key insight. Any physical system that can be in different distinguishable states contains information. A coin sitting on a table contains 1 bit, heads or tails. An electron contains 1 bit in its spin, up or down. A photon contains information in its polarization, its frequency, its direction. In fact, quantum mechanics tells us that every particle, every field, every aspect of reality contains information. And here's what's profound. The behavior of these systems, how they evolve over time, can be understood as information processing. When 2 particles interact, they're exchanging information. When a wave function collapses in a measurement, information is being extracted from the system. This isn't just a useful way of thinking about physics. It's increasingly clear that information is the fundamental thing. Matter and energy might themselves be emergent from informational structures. Think of it like this. Imagine you're playing chess. The chess pieces are physical objects, wooden or plastic, with weight and texture. But what really matters for the game isn't the physical properties of the pieces. It's the informational pattern they represent. Which piece is where, what moves are legal, what the state of the game is. You could represent the same chess game with different physical pieces, or on a computer screen, or even just as a written description. The information is what's real. The physical representation is secondary. Now take this insight and apply it to the universe itself. Maybe the physical properties we observe, mass and energy and charge, are really patterns in underlying information. Maybe electrons aren't fundamental objects, but rather stable informational structures, bits organized in a particular way. This is what it means to say spacetime is emergent. The 3D space we navigate and the flow of time we experience aren't fundamental. They're patterns in information, ways that information organizes itself at macroscopic scales. And if this is true, then the speed of light isn't really about light at all. It's about the maximum rate at which information can propagate through these emergent structures we call space and time. The speed of light is the speed of information. Let me make this concrete with an example from your everyday life. Think about your smartphone. When you're watching a video, information is flowing from the phone's memory to the processor to the screen. There's a maximum rate at which this information can flow, determined by the bandwidth of the connections and the clock speed of the processor. That maximum rate determines how high quality a video the phone can play. Now imagine spacetime works similarly. There's a maximum information transfer rate between neighboring regions of space, determined by Planck scale properties of the underlying informational substrate. That maximum rate is what we measure as the speed of light. It's not that light has a speed limit. It's that information itself has a transfer rate. And light, being pure information, travels at exactly that rate. But what about matter? About electrons and quarks and all the particles that make up atoms? They move slower than light. Why? Here's where it gets really interesting. In the informational framework, massive particles are complex informational structures that require multiple bits to fully specify their state. Moving these structures requires transferring more information than moving a simple pattern like a photon. The mass of a particle is essentially a measure of how much information it contains, how complex its internal structure is. When you try to accelerate a massive particle, you're trying to update its momentum information, which requires information transfer. The more mass it has, the more information needs to be updated, and there's a limit to how fast this can happen. That's why massive particles can't reach light speed. It would require infinite information transfer, which is impossible. Think of it like trying to move files on your computer. A small text file moves almost instantly. A huge video file takes time. The speed limit is the same, but the amount of information determines how long it takes to complete the transfer. Massive particles are like huge files. Photons are like tiny text files. Now, how does this connect to gravity? In the entropic framework, gravity emerges when you have information distributed across space in a non-uniform way. Massive objects concentrate information. This creates information gradients, differences in information density. The second law of thermodynamics, the principle that entropy always increases, really means that information naturally spreads out. It diffuses from high-density regions to low-density regions. When you have a massive object, you have an information concentration. The universe naturally wants to spread that information out to maximize entropy. But here's the thing. The information can't just disappear. It has to be encoded somewhere. In the holographic framework, it's encoded on surfaces surrounding the object. And when another object approaches, the information distribution changes. The system adjusts toward a higher entropy state, and that adjustment causes acceleration. That acceleration is what we call gravity. Let me give you an analogy that makes this tangible. Imagine you have a room with a fire burning in the fireplace. The heat from the fire creates a temperature gradient. Hot near the fire, cooler far away. Now put a cold object in the room. What happens? Heat flows from the room to the cold object, warming it up. But it's not that the heat is attracted to the cold object. It's that the system naturally evolves toward thermal equilibrium, toward maximum entropy. Gravity works similarly in the entropic framework. Massive objects create information gradients. When other objects are present, the system evolves toward configurations that maximize entropy. Objects accelerate toward each other, not because they're attracted, but because that's the direction of increasing entropy. And here's the crucial connection to light speed. This entropic flow, this redistribution of information, can only happen at a maximum rate. Information can't propagate faster than c, so gravitational effects, changes in the gravitational field, also propagate at the speed of light. This is something we've actually observed. In 2017, we detected gravitational waves from two neutron stars colliding, and we also detected the light from that collision. The gravitational waves and the electromagnetic waves arrived at Earth within 1.7 seconds of each other after traveling for 130 million years. This confirmed that gravity and light travel at the same speed. In the entropic framework, this isn't a coincidence. It's inevitable. Both gravitational waves and light are patterns of information propagating through spacetime, and they're both limited by the same fundamental information transfer rate. There are two different types of messages traveling through the same informational substrate at the substrate's maximum speed. But here's where things get truly mind-bending. If spacetime itself is emergent from information, then the geometry of spacetime, its curvature, isn't fundamental either. It's an emergent description of how information is organized. Think about it this way. When you look at a digital photograph on your screen, you see shapes, colors, gradients. But zoom in far enough, and you just see pixels, individual dots of color. The shapes and gradients aren't really there at the pixel level. They're emergent patterns that only appear when you zoom out and look at many pixels together. Spacetime might work the same way. At the Planck scale, about 10 to 35 meters, spacetime might not be smooth and continuous. It might be discrete, pixelated, made of individual informational units. The smooth curved geometry we observe is an emergent pattern that appears when you zoom out and look at many Planck scale units together. This is what physicists call quantum geometry or quantum spacetime. And it's not just speculation. Several approaches to quantum gravity, including loop quantum gravity and certain formulations of string theory, suggest that spacetime is fundamentally discrete at the smallest scales. If this is true, then the speed of light might be analogous to the frame rate of a video game. In a video game running at 60 frames per second, nothing can move more than 1 pixel per frame, or it would create discontinuities, glitches. There's an effective speed limit built into the discrete structure of the game world. Similarly, if spacetime is discrete at the Planck scale, there might be a fundamental limit to how fast information can propagate from one Planck scale unit to the next. That limit manifests at macroscopic scales as the speed of light. And gravity? Gravity is what happens when you have different information densities, different numbers of Planck scale degrees of freedom in different regions. The discrete structure of spacetime naturally creates effective curvature when information is distributed non-uniformly. That emergent curvature is what we experience as gravity. This framework suggests something profound. Space and time aren't fundamental. Information is fundamental. And the laws of physics we observe, including the constancy of light speed and the force of gravity, are emergent properties of how information organizes itself into macroscopic structures. But this raises a question that should be nagging at you. If spacetime is emergent, what about quantum mechanics? Quantum mechanics is our most fundamental theory of how things work at the smallest scales. How does it fit into this picture? Here's where things get really interesting, and where some physicists think we might be on the verge of the biggest revolution in physics since quantum mechanics itself. Quantum mechanics tells us that particles don't have definite properties until they're measured. An electron doesn't have a definite position and momentum simultaneously. A photon doesn't have a definite polarization until you measure it. Before measurement, quantum systems exist in superpositions, being in multiple states at once. This has bothered physicists for a century. Einstein himself never accepted it, famously declaring that God does not play dice, but every experiment ever performed confirms quantum mechanics. The world really does behave this way at the smallest scales. But what if quantum indeterminacy isn't fundamental? What if it's also emergent, arising from the informational structure of reality? Here's the key insight. In the holographic entropic framework, information isn't just stored in the bulk of spacetime. It's primarily stored on surfaces, on holographic screens. When you try to measure a quantum system, you're extracting information from these holographic screens. But there's a limit to how much information can be stored on a given surface area. This is the Bekenstein bound, named after Jacob Bekenstein, who first proposed it. The maximum amount of information that can be contained in a region of space is proportional to the area of its boundary, not its volume. Specifically, there's about 1 bit of information per Planck area, about y-70 square meters. This means that if you try to know everything about what's inside a region, if you try to specify the exact state of every particle, you quickly run up against this limit. There simply isn't enough information storage capacity on the holographic screen to encode all of that detail. What happens when you hit this limit? The universe has to choose what information to store and what to leave indeterminate. The indeterminate aspects are what we observe as quantum uncertainty. Particles don't have definite properties until measured because there literally isn't enough information storage to specify all properties simultaneously. Think of it like a compressed image file. A JPEG image doesn't store the exact color of every pixel with perfect precision. It compresses the information, storing approximations that are good enough for what you see. If you zoom in far enough, you'll find artifacts, places where the compression threw away information. Quantum uncertainty might be analogous, artifacts arising from the limited information storage capacity of spacetime itself. This is a radical idea, and it's controversial, but it suggests that quantum mechanics and the informational structure of spacetime are intimately connected. The uncertainty principle wave-particle duality, quantum superposition. All of these strange features might emerge from the holographic nature of reality. And if this is true, then light speed, gravity, and quantum mechanics are all pieces of the same puzzle. They all emerge from the fundamental informational structure of reality. They're all different aspects of how information organizes itself into the universe we experience. This is the unification we've been searching for. Not just uniting light speed and gravity, but potentially uniting all of physics under a single framework: information. But here's what will really blow your mind. If this framework is correct, it has profound implications for some of the biggest questions in physics and philosophy. Questions like, is time travel possible? What happens inside black holes? Are there other universes? And perhaps most importantly, where do the laws of physics come from? Let's start with time travel, because it's something everyone wonders about, and because the answer reveals something deep about the nature of time itself. In general relativity, certain solutions to Einstein's equations allow for closed time-like curves, paths through spacetime that loop back on themselves. If you follow one of these paths, you'd return to your own past. These solutions exist mathematically, but most physicists believe they're not physically realizable. The universe seems to have a cosmic censorship, preventing the formation of time machines. But why? Why does nature forbid time travel? The usual answer involves paradoxes. If you travel back and prevent your own birth, you create a logical contradiction. But that's not really a physical explanation. It's just pointing out that time travel causes problems. The informational framework offers a deeper answer. Time travel would violate information conservation. If you travel to the past and change something, you're creating information from nothing. The future you came from contained information that the past you arrive in doesn't have. Where did that information come from? In the holographic framework, information is conserved absolutely. It can be transformed, redistributed, encoded in different ways, but never created or destroyed. This is even more fundamental than energy conservation. It's the deepest conservation law. Time travel would violate this law. Therefore, the structure of space-time itself prevents it. Not because of some arbitrary rule, but because closed time-like curves would require information creation, which is impossible in a holographic universe. But here's where it gets interesting. This doesn't quite forbid all forms of time travel. It forbids backward time travel where you can change the past. But what about closed loops that are self-consistent, where everything that happens is already part of a single consistent timeline? In principle, these might be allowed. If a closed time-like curve exists, but information is conserved around the loop, if everything that happens is self-consistent and creates no new information, then there's no violation. The universe might permit these exotic space-time structures. We've never observed anything like this, and it's not clear how they could form naturally. But the point is that the informational framework gives us a principled way to think about these questions. It's not about paradoxes or metaphysics. It's about information conservation. Now let's talk about what happens inside black holes, because this is where the informational framework makes its most dramatic predictions. In classical general relativity, once you cross the event horizon of a black hole, your fate is sealed. You fall toward the singularity, the point of infinite density at the center where space-time curvature becomes infinite. Within a finite time on your watch, you reach the singularity and are destroyed. But Hawking's discovery of black hole radiation changed this picture. If black holes evaporate, emitting radiation, then eventually a black hole will shrink and disappear. What happens to everything that fell in? The information paradox we discussed earlier becomes critical here. If the Hawking radiation is truly thermal, with no information content, then all the information about what fell in is destroyed when the black hole evaporates. This violates quantum mechanics. The resolution in the holographic framework is that the information never really goes inside the black hole. It gets encoded on the event horizon. When you fall into a black hole, from your perspective, you cross the horizon and continue falling. But from the perspective of someone watching from far away, you never quite cross. You get slower and slower, your image getting dimmer and more redshifted, asymptotically approaching the horizon, but never quite reaching it. Both perspectives are real. This is similar to how in special relativity, two observers moving relative to each other both have valid perspectives on simultaneity, even though they disagree about what events happen at the same time. In the holographic picture, what really happens is that your information gets spread across the horizon, encoded holographically. From the outside, you're still there on the horizon, just encoded in a scrambled form. The Hawking radiation gradually carries this information away as the black hole evaporates. This means that black holes aren't really holes in spacetime. They're more like cosmic hard drives, storing information on their surfaces. And when they evaporate, they're slowly transmitting that information back out to the universe. But here's what's truly strange. This suggests that the interior of a black hole might not exist in the way we think. The smooth spacetime continuing past the horizon might be an illusion, an emergent description that only makes sense from the perspective of someone falling in. From the outside, from the holographic perspective, there is no interior. There's only the horizon and the information encoded on it. This is called the black hole firewall paradox, and it's one of the hottest topics in theoretical physics right now. If the holographic principle is correct, then something dramatic must happen at the horizon, something that resolves the tension between the infalling observer's perspective and the external holographic description. Some physicists think there's a firewall, a high-energy barrier at the horizon that destroys anything trying to cross. Others think the interior is connected to other black holes or even other universes through wormholes. Still others think the entire notion of a black hole interior is an approximation. That breaks down when you account for quantum effects. The answer matters because it reveals something fundamental about how space and time work. If the interior doesn't really exist, if it's emergent from information on the horizon, then space itself is more strange and less fundamental than we ever imagined. And this connects back to light speed and gravity. If space is emergent, then the distance between 2 points isn't fundamental. It's a derived quantity, something that emerges from the informational relationships between holographic screens. And the speed of light? It's the rate at which these informational relationships can update. Gravity, in this picture, is the entropic force that emerges when these holographic screens have different information densities. And black holes are just extreme cases where so much information is concentrated that the holographic description becomes obvious, where we can't ignore the fundamental informational nature of reality. Now, let's push even further. If our universe is holographic, if it's really information encoded on some boundary surface, what's on the other side of that surface? Are there other universes? This question leads us to the multiverse, one of the most controversial ideas in modern physics. There are actually several different types of multiverse proposals, and the holographic framework connects to some of them in fascinating ways. The first type of multiverse comes from cosmic inflation, the idea that the very early universe underwent a period of exponentially rapid expansion. Inflation is our best explanation for why the universe is so uniform and flat. But inflationary models suggest that inflation doesn't end everywhere at once. It ends in some regions, creating bubble universes like ours, while continuing in others. If this is true, then our observable universe is just one bubble in an eternally inflating multiverse. Other bubbles would have different properties, maybe different constants of nature, or even different laws of physics. In the holographic framework, each bubble universe would have its own holographic boundary. Our universe is encoded on one boundary, another universe on a different boundary. These boundaries might be causally disconnected, meaning light or information can never pass between them. Each universe is informationally isolated. But here's where it gets really interesting. The holographic principle suggests that our 3D universe might be a projection from a 2D boundary. But where is this boundary? Some formulations of holography place it at infinity, at the edge of the observable universe. But others suggest it could be elsewhere, maybe even in higher dimensions. This connects to string theory, which proposes that fundamental reality has more than 3 spatial dimensions, maybe as many as 9 or 10. The extra dimensions are curled up tiny, too small to detect. But they're real, and physics in these higher dimensions determines what we observe in our 3D world. The holographic principle was actually first formulated precisely in the context of string theory, in something called the ADS-CFT correspondence. This is a mathematical equivalence between a theory of gravity in a higher dimensional space and a quantum field theory without gravity, living on the boundary of that space. Think of it like this. Imagine you have a sphere, a 3D object. Its surface is 2D. Now imagine that everything happening inside the 3D sphere can be exactly described by quantum field theory on its 2D surface. The 3D physics, including gravity, is equivalent to 2D physics without gravity. This isn't just an analogy or approximation. It's an exact mathematical correspondence. And it suggests that our 3D universe might actually be the holographic boundary of a higher dimensional space. If this is true, then the question, what's outside our universe, has a precise answer: higher dimensional space. We're living on the boundary of something bigger, and our 3D reality is a projection of physics happening in that higher dimensional realm. But here's what will truly melt your brain. If our universe is a holographic projection, then the distinction between inside and outside, between our 3D world and the higher dimensional space, might not be meaningful. You're sitting somewhere right now, watching this video. Maybe you're on a couch, maybe on a bus, maybe lying in bed. You feel solid. The chair beneath you feels solid. The air around you seems like empty space. Time flows steadily from past to future. These seem like the most basic, undeniable facts of existence. But if the informational framework is correct, none of this is quite what it seems. The solidity of matter? That's electromagnetic forces between atoms, which are really patterns in quantum fields, which are really informational structures encoded holographically. The chair isn't solid in any absolute sense. It's a stable pattern of information that interacts with a stable pattern of information. That is your body in a way that prevents interpenetration. The empty space around you? It's not empty at all. It's seething with quantum fluctuations, virtual particles popping in and out of existence. Spacetime itself potentially discrete and granular at the smallest scales. Every cubic centimeter of empty space contains enormous amounts of information encoded holographically. The flow of time? That might be an emergent phenomenon too. At the fundamental level, the laws of physics are time-symmetric. They work the same forward and backward in time. The arrow of time, the fact that you remember the past but not the future, might arise from the increase of entropy, from information spreading out and becoming more scrambled. Think about it. You remember the past because your brain contains organized information about past events. Memories are low-entropy information structures. The future is uncertain because high-entropy states have many possible configurations, while low-entropy states have few. The arrow of time points in the direction of increasing entropy, of information becoming more spread out and less organized. So the flow of time you experience, the most immediate and certain thing about your existence, is actually an emergent property of information dynamics. Time isn't fundamental. It's a macroscopic pattern. This might sound abstract, but it has concrete implications. For one thing, it suggests that at the deepest level, past and future aren't fundamentally different. They're both just directions in the informational structure of the universe. The reason they seem different to you is because you're a localized, low-entropy information structure, a human brain, experiencing one particular slice through this structure. But here's what's really profound. You are information. Not metaphorically, literally. Your body is a pattern of atoms, which are patterns of quantum fields, which are informational structures. Your thoughts and memories are patterns in neural connections, which are also ultimately informational structures. The you that exists right now is a particular configuration of information, highly organized and self-aware. And the fact that you're self-aware, that you can reflect on your own existence, means your information that has become complex enough to process information about itself. You're a recursive loop of information processing. You're the universe experiencing itself, understanding itself through a localized informational structure evolved to survive and reproduce. This isn't diminishing or reductive. It's actually incredibly profound. It means that consciousness, awareness, your subjective experience of being you, emerges from the same informational substrate as everything else. You're not separate from the universe. You're a pattern in the universe, a way the universe organizes itself. And if the holographic principle is correct, then in some sense, you're encoded on the boundary of the observable universe. All the information about you, every thought you've ever had, every decision you've ever made, is out there on a cosmic holographic screen, part of the informational structure of the cosmos. This connects to something physicists call the observable universe versus the universe as a whole. You can only see out to the cosmic horizon, about 46.5 billion light years away. That's not because the universe ends there, but because light from farther away hasn't had time to reach you yet, given the age of the universe and its expansion. In the holographic framework, this cosmic horizon is real and significant. It's the boundary on which information about your observable universe is encoded. Everything you can ever observe, everything that can ever influence you, is contained within this horizon, and all of that information is holographically encoded on its surface. You are, in a very real sense, contained within your cosmic horizon, and the physical laws you observe, including the speed of light and the nature of gravity, emerge from how information is organized on this horizon. Different observers with different horizons would have slightly different holographic encodings. The universe as experienced by someone in a distant galaxy beyond our cosmic horizon is informationally separate from our universe. We share the same underlying reality, but our observable universes don't overlap. We're informationally isolated. This has a beautiful implication. There's something special about your reference frame, your location in space and time. Not because you're at the center of the universe in any privileged sense, but because the universe you observe is uniquely yours. The particular slice of reality accessible to you, the particular holographic horizon you're within, defines a unique perspective on existence. And yet, paradoxically, you're also connected to everything. The information that makes up you interacts with the information around you constantly. Every photon that hits your eye, every air molecule that enters your lungs, every gravitational tug from distant galaxies, these are all information exchanges. You're in constant communication with the cosmos. The speed of light, that cosmic speed limit we've been discussing, determines how fast information can flow between you and the rest of the universe. It's why you see the sun as it was 8 minutes ago, why distant galaxies appear in their ancient past. But it's also what allows you to exist as a coherent, stable information structure. If information could travel infinitely fast, if there were no light speed limit, then you couldn't exist as a localized entity. Information from everywhere would be affecting you instantaneously. There would be no separation, no individuality. The speed limit is what creates the possibility of distinct, individual conscious beings. And gravity? Gravity is what keeps you together, what prevents the information structure that is your body from dispersing. But it's not pulling on you in the classical sense. It's an entropic effect, a consequence of how information wants to distribute itself to maximize entropy. The fact that you're held to Earth's surface is the universe finding its highest entropy configuration given the presence of Earth's mass. You being on the ground has more possible microstates, more ways for information to be arranged than you floating in space. So entropy naturally pushes you downward, and you experience this as gravity. This might seem strange or counterintuitive. Isn't my organized body lower entropy than me being dispersed? Yes, but we're talking about the entropy of the total system, including all the holographic screens and information distributions in the surrounding spacetime. Your organized body on Earth's surface is part of a higher total entropy configuration than your organized body floating in space. But here's what I really want you to understand. The fact that you exist at all is extraordinary. You're a highly organized, low-entropy structure in a universe that's constantly moving toward higher entropy. You're a local violation of the second law of thermodynamics, sustained by constant energy input from food and oxygen. Every moment of your existence represents a triumph of organization over disorder, of information preservation over information scrambling. You're a temporary eddy in the river of entropy, a pattern that maintains itself for a brief time before eventually dispersing back into the cosmos. And yet, in the holographic framework, the information that is you is never truly destroyed. It persists, encoded on holographic screens, redistributed and scrambled, but never lost. In a profound sense, you're eternal. Not as the conscious, self-aware you, but as information that was once organized into that pattern. This raises deep philosophical questions. What is the relationship between you and the information pattern that constitutes you? If that pattern could be copied exactly, would the copy be you? If the pattern persists after your death, scrambled and redistributed, is there a sense in which you continue to exist? These aren't just philosophical puzzles. In a world where the informational nature of reality is understood, where we might eventually be able to manipulate information at fundamental scales, these questions become practical. If we could read out the information encoded on holographic screens, could we reconstruct the past? Could we preserve the information pattern of a person and restore it later? I'm not saying any of this is possible with current or near-future technology, but the framework suggests it's not impossible in principle. Information is conserved. It's all still out there, encoded holographically. The question is whether we could ever develop the technology to access and manipulate it. But let's bring this back to the present, to your life right now. What does understanding this framework give you? How does it change anything about how you live? Here's what I think is most important. It reveals that reality is far stranger, far more wonderful than our everyday experience suggests. The mundane world of objects and forces is just the surface. Underneath is a cosmos of information, of holographic encodings, of emergent spacetime and entropic forces. You are part of that cosmos. You're not separate from it, observing from the outside. You're a pattern within it, a way it organizes itself. And everything you do, every choice you make, every thought you have, is part of the informational evolution of the universe. This can be empowering or terrifying, depending on how you look at it. Terrifying, because it suggests that the solidity and permanence we crave is illusory. Everything is patterns in information, subject to change and eventual dissolution. The you that exists today is not exactly the same information pattern as the you that existed yesterday or will exist tomorrow. You're constantly being recreated, moment by moment. But it's also empowering because it reveals that you have genuine novelty, genuine creativity. The patterns you create, the information structures you build through your choices and actions, are real additions to the informational content of the universe. You're not just a passive observer. You're an active participant in the cosmic evolution of information. And perhaps most importantly, understanding this framework cultivates humility and wonder. Humility because it shows how much we don't know. Everything I've described is at the frontier of physics. Much of it is speculative, unproven, possibly wrong. We're like explorers mapping the edges of a vast continent. Having sketched the coastline, But knowing that enormous territories will also be able to use gravitational lensing, the bending of light around massive objects, to map where mass actually is in galaxies and galaxy clusters. Dark matter theories predict that most mass is in an invisible halo. Entropic gravity predicts that all the mass is in the visible stars and gas, with the extra gravitational effect coming from the entropic modification. These tests are happening right now. The data is being collected as I speak. Within the next few years, we'll know whether entropic gravity's predictions about galaxy dynamics hold up or not. The third test is more subtle, but potentially even more profound. It involves quantum mechanics and the interface between quantum systems and gravity. If spacetime is emergent from information, then at some scale, the smooth geometry of general relativity must break down. There should be signatures of the underlying discrete informational structure. These signatures might appear as tiny violations of the equivalence principle, the rule that all objects fall at the same rate regardless of their composition. The equivalence principle is one of the most precisely tested principles in physics. We've confirmed it to better than 1 part in a trillion. But all these tests have been done with macroscopic objects. What about quantum systems? Several groups are now developing experiments to test the equivalence principle with quantum objects, things like atoms in superposition states or entangled particles. If spacetime is emergent, if it arises from information, then quantum objects might interact with gravity in slightly different ways than classical objects. The deviation would be tiny, but potentially detectable. One particularly exciting experiment involves putting a quantum system, like a superconducting qubit or a trapped atom, into a superposition of 2 locations at slightly different gravitational potentials. If spacetime is truly emergent from information, then the gravitational field itself might behave differently when interacting with a quantum superposition versus a classical object. Think of it like this. A classical object has definite information about its location. A quantum superposition doesn't. If gravity emerges from information distribution, then a quantum superposition might create a different informational configuration than a classical mixture, leading to measurable differences. These experiments are incredibly difficult. You're trying to measure quantum effects in gravity, which is by far the weakest force. It's like trying to hear a whisper during a thunderstorm. But several labs around the world are working on it, and within the next decade, we might have results. The fourth test involves black holes, specifically the information content of their event horizons. According to the Bekenstein-Hawking formula, the entropy of a black hole is proportional to the area of its event horizon. This entropy represents information. But what exactly is this information? In the holographic framework, it should be the complete information about everything that fell into the black hole encoded on the horizon. And if that's true, then the Hawking radiation emitted as the black hole evaporates should carry this information back out. Recent theoretical work by Stephen Hawking, Leonard Susskind, and others suggests that the Hawking radiation does indeed contain information, but it's scrambled in an incredibly complex way. Unscrambling it would require observations and calculations far beyond what we can currently do. However, there might be shortcuts. Some physicists think that if we could observe a black hole throughout its entire evaporation, from formation to complete disappearance, we might be able to detect statistical signatures in the radiation that reveal the informational structure. This is purely hypothetical for stellar mass black holes, which take about 1,067 years to evaporate. But there might be primordial black holes, tiny black holes formed in the early universe that are evaporating right now. If we could detect one of these in its final moments, when it's radiating away its last bits of information, we might learn something profound about the holographic nature of reality. This is a long shot. We've never detected a primordial black hole, and we don't know if they exist. But telescopes are searching, and if we get lucky, we might see one explode in a burst of Hawking radiation. The fifth test is cosmological. Entropic gravity makes predictions about dark energy, the accelerated expansion of the universe. Specifically, it predicts that the acceleration should have a particular relationship to the matter content of the universe and the size of the cosmic horizon. We're already testing this with observations of distant supernova, the cosmic microwave background, and large-scale structure. The data so far is consistent with both standard dark energy and entropic gravity predictions, but the error bars are still too large to definitively distinguish them. However, upcoming surveys like the Dark Energy Spectroscopic Instrument, DESI, and the European Space Agency's Euclid mission are mapping the universe with unprecedented precision. They're measuring exactly how the expansion rate has changed over cosmic history. Within the next 5 to 10 years, we'll have data precise enough to test whether the acceleration follows the pattern predicted by entropic gravity, or whether it requires a cosmological constant or some other form of dark energy. This will be a crucial test. But here's what I want you to understand. Science doesn't move in discrete jumps from wrong theory to right theory. It moves gradually, with new theories refining and extending old ones, valid in new regimes, or providing new insights. Even if every test I just described supports entropic gravity, it won't mean general relativity was wrong. Einstein's theory will still be correct in the regimes where it's been tested. Entropic gravity would be an extension, a deeper understanding that reduces to general relativity in appropriate limits, just as general relativity reduces to Newtonian gravity in the weak field limit. And even if some tests contradict entropic gravity, that doesn't mean the holographic informational framework is wrong. It might mean Verlin's specific formulation needs modification. Other physicists might develop alternative versions that work better. This is how science progresses. Not through sudden revolutions where everything changes, but through gradual refinement, with different frameworks providing complementary insights. What matters is that we're asking the right questions and developing ways to answer them. The question, are light speed and gravity unified in an informational framework, is now a scientific question, not just a philosophical one. We have theoretical predictions and experimental tests. That's enormous progress. But let me tell you about something even more speculative, something that pushes to the very edge of what we can reasonably discuss. What if we could manipulate the informational structure of spacetime? If spacetime is emergent from information, if gravity is an entropic effect, then in principle, you could modify gravity by manipulating information distribution. You could create artificial gravitational fields, or shield against gravity, or perhaps even warp spacetime in controlled ways. This sounds like science fiction, and with our current understanding and technology, it absolutely is. We can't manipulate information at the Planck scale. We can't control the holographic encoding of spacetime. We barely understand what that even means. But here's the thing. 100 years ago, the idea of nuclear energy was pure speculation. 50 years ago, quantum computers were a theoretical curiosity. Today, we're splitting atoms to power cities and building quantum computers that can solve certain problems exponentially faster than classical computers. The trajectory of technology follows understanding. Once we understand how something works at a fundamental level, we eventually develop the ability to manipulate it. It took decades to go from understanding nuclear physics to building reactors, but we got there. If we truly understand that spacetime is emergent from information, that gravity is entropic, then someday, perhaps centuries from now, we might develop technologies that seem magical to us today. Not faster than light travel, because that would violate information causality, but perhaps artificial gravity, controlled spacetime curvature, maybe even the ability to create pocket universes with different properties. This is wild speculation. I'm not saying any of this will happen. I'm saying that understanding the fundamental nature of reality opens doors we can't yet imagine. Every deep insight in physics has eventually led to technology. Maxwell's equations led to radio, electric power, and telecommunications. Quantum mechanics led to transistors, lasers, and computers. General relativity enables GPS. What will the informational understanding of spacetime lead to? We don't know. But history suggests it will be something. And here's what's really exciting. You're alive at the beginning of this journey. You're watching as the first pieces of this puzzle are being put together. Future generations might look back at this era the way we look back at the early 20th century, when Einstein and others were first grappling with relativity and quantum mechanics. They were living through a revolution in understanding, even if they didn't fully realize it at the time. You might be too. So let me ask you, does this excite you? Terrify you? Both? Drop a comment with your reaction. Because this is where science becomes not just about understanding, but about possibility, about futures we can barely imagine. Now, I want to address something important: criticism and skepticism. Because I've presented this informational framework enthusiastically, but I need to be clear that many physicists are skeptical. There are legitimate criticisms and open questions. First, the mathematical rigor. Verleen's entropic gravity is mathematically sophisticated, but some physicists argue it's not yet as complete or rigorous as general relativity. There are situations where the equations become ambiguous, or where it's not clear how to apply them. This doesn't mean the theory is wrong, but it means more work is needed. Second, the dark matter question. I mentioned that entropic gravity might explain galactic rotation without dark matter, but there's other evidence for dark matter beyond rotation curves. Gravitational lensing, the cosmic microwave background, galaxy cluster dynamics, all of these seem to require dark matter. Verleen and others argue that entropic gravity can explain these observations too, but the details are still being worked out. Some observations are easier to explain than others. This is an active area of research and debate. Third, the quantum mechanics connection. The idea that quantum indeterminacy emerges from limited information storage is intriguing, but it's not yet a complete theory. Standard quantum mechanics is incredibly well tested, and any modification needs to reproduce all its predictions in the regimes where it's been verified, while making new predictions elsewhere. Some physicists think the informational framework might eventually provide this, but we're not there yet. We don't have a complete quantum theory of gravity that fully incorporates holographic principles and makes testable predictions different from standard approaches. Fourth, the holographic principle itself, while strongly supported by theoretical considerations from black hole physics and string theory, hasn't been directly experimentally verified. We've never measured the information content of a region and confirmed its scales with area rather than volume. This is something we hope to test, but it remains theoretical for now. These are real issues. Science progresses through a combination of bold new ideas and rigorous criticism. The informational framework is bold. The criticism is pushing it to become rigorous. But here's why I think this framework is worth taking seriously. Even with these open questions, it provides a conceptual unification that feels right. It takes disparate phenomena, light speed, gravity, quantum mechanics, black hole thermodynamics, cosmological observations, and shows how they might all emerge from a single underlying structure. This doesn't prove it's correct. Nature doesn't care about conceptual elegance. But historically, when physicists have found deep unifying principles, they've usually been onto something real. Maxwell unified electricity and magnetism. Einstein unified space and time. The Standard Model unified 3 of the 4 fundamental forces. Each of these unifications started with theoretical insight and conceptual elegance, then gradually accumulated experimental support. The informational unification might be following the same path. Or it might not. It might turn out to be a beautiful idea that doesn't match reality. That happens too in science. The luminiferous ether was a beautiful idea that turned out to be wrong. Steady-state cosmology was elegant, but didn't match observations. Science is self-correcting. Wrong ideas eventually get pruned away by experiment and observation. What survives is what matches reality, regardless of how elegant or intuitive it seems. So where does that leave us? We're at a moment of possibility. We have a framework that might unify light speed and gravity. That might explain mysterious observations. That might reveal the fundamental informational nature of reality. But we don't yet know if it's correct. The next decade will be crucial. The experiments and observations I described will either support this framework or refute it. We'll either see evidence of entropic modifications to gravity in galaxy rotation and gravitational waves, or we won't. We'll either detect signatures of emergent spacetime in quantum gravity experiments, or we won't. This is the exciting thing about living through a potential paradigm shift. You don't yet know how it will turn out. Future textbooks might describe the informational framework as one of the great breakthroughs in 21st century physics. Or they might mention it as an interesting idea that ultimately didn't pan out. But either way, the questions being asked are profound. Either way, we're pushing toward deeper understanding. And that's what matters. Now, let me bring this to a conclusion by connecting everything we've discussed back to you, to your life, to why any of this matters beyond the realm of abstract physics. We started with a simple question. Could a new theory unify light speed and gravity? And we've seen that the answer might be yes, through the lens of information and holography. But the deeper question is, what does this mean for how you understand reality and your place in it? Here's what I think is most important to take away from this journey. First, reality is stranger than it appears. The solid, stable world of everyday experience is a macroscopic approximation. Underneath is a cosmos of information, quantum fields, emergent spacetime, and holographic encodings. You don't need to understand all the technical details to appreciate this profound strangeness. Second, you are part of this cosmic information structure, not separate from it, but woven into it. Every thought you have, every choice you make, every interaction you experience is part of the informational evolution of the universe. You matter in the most literal sense. You are information that matters, that has consequences, that shapes the future. Third, we live in an age of discovery. The questions we're exploring about the nature of space-time, information, and reality are as profound as any questions humans have ever asked. And we're making genuine progress. The experiments and observations of the next few decades might revolutionize our understanding of existence itself. Fourth, science is a human endeavor. It's not some abstract, impersonal process. It's people asking questions, developing ideas, arguing with each other, testing predictions, celebrating successes, and learning from failures. By engaging with these ideas, you're part of this human endeavor to understand the cosmos. And finally, wonder is important. It's easy to get caught up in the mundane details of daily life, to forget that you're a temporary pattern of information on a small rocky planet orbiting an ordinary star in an ordinary galaxy in a universe of incomprehensible scale and strangeness. But you are. You're part of something vast and amazing. The atoms in your body were forged in stars. The information that constitutes you has existed in various forms since the Big Bang. You're made of stardust, quite literally, organized into a configuration that can think and feel and wonder about itself. The speed of light connects you to the cosmos. Every photon that enters your eye has traveled at exactly that cosmic speed limit, carrying information from the world around you. The gravity that holds you to Earth is an entropic effect, the universe finding its highest entropy configuration, but it feels like home, like the natural order of things. You live at the intersection of the quantum and the classical, the microscopic and the cosmic. You're large enough that quantum effects average out into classical behavior, small enough that you can hold the entire observable universe in your thoughts. This is extraordinary. This is precious. And understanding it more deeply, seeing how light speed and gravity might emerge from information, how space-time might be holographic, how you might be a pattern in the cosmos rather than separate from it. This deepens the wonder rather than diminishing it. So here's my final question for you. What will you do with this understanding? How will it change how you see yourself and the world? Will you look at the sky differently, knowing that the light from those stars is information traveling at the cosmic speed limit? Will you feel the ground beneath your feet differently, knowing that gravity is an entropic effect emerging from holographic information? Will you see yourself differently, as a temporary but real pattern in the informational structure of the cosmos, connected to everything, part of the ongoing evolution of reality itself? I hope so. I hope this journey has given you not just knowledge, but a new perspective, a sense of wonder and connection that enriches your experience of being alive. Because that's ultimately what science is for. Not just to make predictions or build technology, though it does those things, but to deepen our understanding of what we are, where we come from, and what reality is. We are the universe understanding itself. We are information processing information. We are patterns in spacetime wondering about spacetime. And that's beautiful. Thank you for coming on this journey with me. Thank you for stretching your mind to encompass these strange and wonderful ideas. Thank you for being part of this collective human endeavor to understand the cosmos. If this video has meant something to you, if it's changed how you see reality even a little bit, then hit that like button and subscribe. Share it with someone who loves to think about big questions. And most importantly, drop a comment. Tell me what struck you most, what questions you still have, how this has affected your worldview. Because this conversation doesn't end here. It continues in the comments, in your thoughts, in how you carry these ideas forward into your life. We're all part of this together, exploring the nature of reality, one insight at a time. The universe is stranger and more wonderful than we ever imagined. Light speed and gravity might be two faces of the same informational reality. Space-time might be emergent and holographic. You might be a pattern in the cosmos, temporarily coherent, ultimately eternal as information. And we're just beginning to understand it all. What a time to be alive. What a gift to be conscious and curious in a universe that rewards curiosity with insight. Until next time, keep wondering, keep questioning, and keep exploring the magnificent mystery of existence.